Good day. I'm Kyrylo Malakhov from Glushkov Institute of Cybernetics. Thank you for joining me. Today I'll show you how we can run capable open large language models on CPU-only environment using llama.cpp toolchain with 4-bit quantization. I'll share benchmarks across three CPU environments, a bilingual case study and project called MedLocalGPT, and a practical deployment tips for cost-sensitive scenarios. I'm excited to exchange ideas with you, so let's dive in. First of all, let me position this work. We target three drivers: cost and availability, CPU you already owned, privacy and governance, keeping data on prem, and portability, a lean, reproducible stack. Important to note that our operational task in this project was to run LLMs in a CPU-only environment, no GPUs under realistic cost-constrained conditions. Our purpose is threefold. First, to measure throughput, time to first token, and memory footprint for from 1 up to 24 billion instruction-tuned models running CPU only with Llama CPP 4-bit quantization. Second, to map the sweet spots between model size and available cores so you can choose what's viable for interactive use on legacy Xeon processor, modern Xeon processor, and modern laptop CPU, and this third, to validate practically by developing a bilingual medical assistant called MedLocalGPT that combined English Ukrainian Ukrainian English translation with RAG grounded QA system, retrieval augmented generation QA system, end to end on CPU. Concretely, we evaluate 7 models across 3 CPU classes environments to demonstrate this assistance that's suitable for clinical knowledge access without GPUs. So next up, we talk about models and runtime stack. In this study, I evaluate 7 instruction-based models from 1 billion up to 24 billion parameters spanning translation, Q&I, and reasoning tasks. So on the slide, you can see title of the models and short description. And here we can see that all models are multilingual, but except 2 models that didn't support Ukrainian language. So important information that the Llama CPP tool compiled with Intel One API compilers inside a specialized Docker container derived from the Intel One API based toolkit image, which gives us a consistent 1 MKL blast and runtime stack for reproducible CPU performance. Also, I need to note that all models' weights were converted to GGUF and quantized to 4-bit for memory efficiency using the script that ships with Llama CPP. The name script is convert HF to GGUF.py. So next up, we talk about hardware environments, and in this study covered 3 representative CPU environments. First is a self-hosted Intel Xeon E5 processor. This represents the kind of legacy servers still common in universities or hospital data centers. Second, and an Intel Xeon modern CPU uh, hosted on Amazon Web Services EC service. and the third one, a modern laptop, Intel Core i7 CPU. Also, I want to note that for cross-platform fairness, I run benchmarks in a uniform default profile. This profile is consisted of 16 virtual CPUs, 32 gigs of RAM, 256 gigs of storage, Alpine Linux for base OS, and on the laptop I pinned the process to 16 threads to mirror the same thread budget, and in all cases I pinned threads to physical cores to reduce jitter. So next up we talk about results, performance results. For these numbers, I use Llama Bench from the llama.cpp toolchain. It let us benchmark both prompt processing speed and text generation speed separately, and it reports time to first token, so we can see the front-loaded cost of encoding the prompt versus the steady-state streaming rate. So we can see obviously modern AWS Xeon CPU is clearly on top of the line. However, the old Xeon E5 and the laptop i7 CPU still deliver practical interactive performance, fast enough for responsive chatbot, rec assistants, and even nearly real time sentence level translation. So next up we can see the memory footprint of the models. The big idea here is 4-bit quantization, is that we store each weight in 4 bits instead of 16. So models are really 4 times smaller while staying usable for inference. What does it mean in practice? On 32 gigs of RAM virtual machine, you can comfortably run 24 billion model or two small models from 1 to up to 8 billion side by side with a vector store database for rack. On 16 gigs of RAM virtual machine, you need to stick with 1 up to 8 billion models for the best headroom. And remember, there is more than the weights. The key value cache grows with the context length and batch size. So it must be keep from 25 to 30% of free RAM for the key value cache and the OS with typical chat or rec prompts that enough to keep everything responsive on CPU. So next up we talk about MedLocalGPT project. Here you can see simple C4 style block diagram. MedLocalGPT runs entirely on CPU. I composed two small models, Phi for Mini for bidirectional translation English-Ukrainian. This is AI agent for translation, and I use Gemma 311 billion for domain QA AI agent for retrieval augmented generation. So a rec pipeline uses instructor large embeddings and ChromaDB over rehabilitation medicine corpus composed from EBSCO database of peer review articles. So on a 16 virtual CPU with 32 gigs of RAM, typically short grounded answer arrive in 2.5 up to 4.5 seconds on older Xeon CPU and under 2 seconds on the newer Xeon. This meets interactive and expectation while keeping data on-prem. So I want to tell you about that MedLocalGPT is available as a web app and Telegram bot. Is available for English and for Ukrainian language, and you can join the GitHub repo by the following QR code. So next up, I want to talk about limitation and what's next. This study emphasized throughput, latency, and footprint. We did not report quality metrics here, and we fixed on llama.cpp 4-bit quantization with a specific virtualization stack. Next, we will extend to quality and safety evaluations, of course, efficiency attention for long context, and retrieval interleave generation over SparkQL with ontology-guided knowledge access. We also plan cost energy profiles and long horizon stability tests. So I want to share with you some words about the next generation of our chatbot. We will use the knowledge base uh, upon on the Apache Gemma Fuseki triple storage. We use SparkL templates and some transformer model for choosing and classification these templates according users natural language request to the system, and we use some LLMs for AI agent that uh, will be only compile the answer of our system, not using the LLM's knowledge, but using the knowledge that we can get from our uh, Apache Gemma Fuseki triple storage to present the natural language pretty answer to user. So to close my keynote, I want to acknowledge the funding and people who made this work possible. This research was supported by a contract with Gorbachevsky Chernobyl National Medical University entitled Development of an AI-based decision support expert system prototype. This contract is a part of the big national R&D initiative of Ministry of Education of Sciences and Chernobyl National Medical University entitled Development of Personalized Telediagnostic Platform with AI. Also, I want to know that this study was a part of two National Academy of Sciences of Ukraine projects, theoretical foundation and functional models of a computer processing complex information structure, and develop means of supporting virtualization technology, etc. So these two projects conducted in Glushkov Institute of Cybernetics. Also, I want to special thanks to my scientific supervisor, academician Alexander Palagin, and project supervision and guidance by Professor Dmytro Vakulenko from Chernobyl National Medical University and Dr. Mykola Budnik from Glushkov Institute of Cybernetics. Also, I want to thanks to workshop organizer, especially Dr. Dmytro Chumachenko. So, thank you for your attention. Here you can see my contacts. If you want to ask me, you can just scan QR code and get all info about me and my project. So thank you for your attention.